we have a so-called compressibility factor. Okay, what's that? It's a factor that accounts for the deviation of real gases from the ideal gas behavior at a given temperature and the pressure. Okay, so because in most cases we cannot simply use the ideal gas equation because properties does not exactly match those for the ideal gas case. So we need to include one more factor here to make the results to be more accurate. Okay, we will add one more factor inside this ideal gas equation. PV equal to Ez RT. So the Ez is equal to defined as the V actual divided by the V ideal. Okay, by the V ideal. This V of course is the actual volume. If you just plug in this one, and you will see that the V actual cancels and it will become the ideal gas equation. Okay, so in this case, we will also include this one to be the compressibility factor, and we compute this equation. For the ideal gas, the Ez is equal to 1, so we can again get the ideal gas equation. And the V actual will be equal to V ideal. Okay, so here this figure shows you the picture. Okay. In order to find out the compressibility, it's quite difficult if you just consider just the absolute pressure as well as the absolute temperature. The reason is that for different pure substances, we have different properties. As a result, we will introduce two terms here. One is the reduced pressure. It's defined as PR equal to P divided by the P critical. The P critical is the critical pressure I have shown you in section 3.3 when I talk about the property diagram. Okay. This subscript R just means reduced, so this one is a reduced pressure. Similar definition for the reduced temperature. Okay. And we can see that all gases will have approximately the same Ez value for the same reduced pressure and the temperature. Okay. Although the gas will have different properties due to their molecular structure, if we get this reduced pressure, reduced temperature, then they will get approximately the same Ez value. That's called the principle of corresponding state. Okay? And because of this result, it leads us to make a so-called compressibility chart. So here we have a lot of points showing the actual result, showing the actual data of different kinds of gases. For example, here we have methane, ethylene, ethane, propane, etc. Okay? So here the curves are based on the data of hydrocarbon as well as water. And we also have nitrogen in this case. And here, for this chart, we have several approximations. Is that if the reduced pressure is very small, for example, is very close to 0, then all of the points would go to 1. Okay? That means for very low pressure, it will be very close to the ideal gas behavior. And if you increase the temperature, for example, here is 1, 1.1, 1.2, etc., until we go to PR equal to 2. You will see that the graph, gradually it will be much closer to the value of 1. That's our observation. At a higher temperature, the gas will be closer to this so-called number 1, which represents the ideal gas behavior. Okay? So we will have the greatest deviation from the ideal gas behavior around the critical point. Here, this is the greatest deviation. And after that, it will be closer to 1, more closer to 1, etc. So we'll have this regime of the points, especially at TR equal to 1, then this trough would have a reduced pressure of approximately equal to 1. So near the critical point, we have the greatest deviation. Okay. So here, I've talked about this, observations shown here. Okay. However, sometimes we may not get the information for either P or T given. Okay? That means maybe we just have the P or we just have the T, but we have the specific volume here. It's more convenient to define the pseudo-reduced specific volume. What do we mean by the pseudo-reduced? Is that you can see from this formula, VR equal to V actual divided by this bunch of things. But what is this? Well, this RT divided by P is just the critical volume, okay? So we can get the volume by this formula and check out the table. So because of this, we also include the VR curve in a very messy diagram. The messy diagram is actually in your figure A15, and I also have a copy listed here But you will see that because this is in black and white printing, so you will see that the grid lines as well as the curve will have a very similar color and you cannot see it clearly. Let me give you the color version, although it's also messy. So this is actually a clearer curve. In general, I would say for 90%, okay, it will just appear in your homework. Okay, for your exam, it will have a less chance to include the compressibility factor in your problem. Okay, because it's extremely tedious to get a value. Okay, and we need to use very much time. Okay, but I need to also introduce this to you because it may appear in your homework. Okay, so I will demonstrate how to use this compressibility chart in the next example.